All right, so here we're looking at the number of general aviation aircraft annually for the accidents from 1975 to 1997, and it's modeled by this function here. Again, X is the number of years since 1975. So we're supposed to calculate, excuse me, the average rate of change in the yearly number of accidents from 76 to 97. Well, if this is from 1975, 1976 has to be a 1, and 1997 then is going to be 22. So that's a key thing we need to start from. Calculate the average number of accidents that occurred each year from 76 through 97, and then graphically illustrate the answers to part A and part B. All right, so part A. Average rate of change. Well, remember, we can just plug in and say, well, we want to take A of 22, if I can write, A of 22 minus our A of 1 divided by our 22 minus 1. Now, we could plug all that in, and if we do that, let's go to our calculator. I've got the equation here already, so let's do a trace, and let's do a 1. Actually, you know what we could do even better? Let's go back over here, and we can clear that. We can just take and plug in and take the value. Let's just do it this way. It's going to be easier. Let's do value and do 22, write it down. Oop, not 222. 1754.0976. Okay, we need a value of 13866.9454. All right, so now what we can do, take our value, 1754.0976 minus 3866.9454, and then that whole thing divided by 21, because 22 minus that. So we get a negative 100.6118. All right, so this is equal to negative 100.6118, I think it was. No, I forgot, but I think that's right. And that's going to be in accidents per year. Because we have years down here, and this is accidents. So that's the average rate of change. Now, B, calculate the average number of accidents. Well, that's going to be, now we're going to take our integral from 1 to 22 of our A of x dx and divide that whole thing by 22 minus 1. Okay, so now that one we can plug in easily. So we're just going to take math, 9, 1 to 22 of 1, and then we'll put in x. And then that's divided by 22 minus 1, which is 21. And we get a value of 2,810.5215. So that was 2810.5215. And this is just plain old accidents. Okay. And so with that, then basically, let's think about here what we have. So if we're going to graph this, we're going to have our original function that's a linear is going down. So it's going to come down like this. And this is going to be a big number up here. I don't know what 0 would be, but it's going to be 3967.5572. This one I'm not going to plug in and solve for 0 there, but and then we're going to have something. If that's 39, so that's going to be maybe about right here. That's going to be the 2810.5215. So that place there, that's going to be kind of our intersections, okay? And so if we solve that, we could do math, numeric solver, and we could say, when is it? The 2810.5215, and we can then do our next part. Well, it's y1. Actually, it's let's see. I don't think that's right. Yeah, that is. Okay, so that one is a curve. Yeah. So 11.5. So, well, go back. There we go. So this is at 11.5, and so that's 11.5 comma 2810.5215. Okay, and so that's our intersection. So graphically illustrated, this is our average number of accidents, and it's going to occur, both of them are going to intersect at 11.5, and that's going to be years since 1975. Okay. So what was this one? This is our slope. Slope is equal to a negative 100.6118, and that's our average rate of change, which is what we found here. So even though we plotted the actual line, we note that our average rate of change, which is what we calculated in the first one, is equal to our slope. Okay, so that's kind of a key thing there. Slope is that, but that's also the average rate of change. So those two things are kind of nice to see how they come into play with both of those parts. What about vegetable consumption? So the per capita consumption of commercially produced fresh vegetables in the US from 1980 to 2000 can be modeled as that function. And what was the average per capita consumption of commercially produced fresh vegetables in the US between 80 and 2000? All right, so 1980, well, that was when it started. So if we plug that into our thing, that's 0, and that's 20 years later. So we need to know those to make sure we have a problem. Okay, so that's the average per capita consumption. So A is just going to be our integral from 0 to 20 we just looked at, and that's going to be our v of t dt, and we're dividing that whole thing by the 20 minus 0. Okay, so let's go check that out. Now clear, I have to quit. Now this one, I put both equations for part 1 and part 2, and so this one is actually the one we're going to use now, and we can turn that one off. And so our function looks like that. Let's maybe bring it back down a little bit, maybe into, I don't know, 200 by 50, see what that looks like. That's too much down. So let's go here, maybe minus 20. And so that's kind of what we're looking for here. And if we were actually, if we go out to 22, that should give us enough we need. There we go. So now we have pretty much the whole picture. All right, so what we're going to do is we're going to do our math, and we're going to go from 0 to our 20. And this is in y2 of dx. We're dividing by 20 minus 0, which is just 20. So the first one is 169.021. So if we plot that point, 169.021, we can kind of see where that intersects it. So that's kind of a key point, because sometimes we need those. So that's equal to the 169.021, and that's going to be in pounds. Okay. Now, what was the average rate of change in per capita consumption between there and there? Well, that's going to be our V of 20 minus our V of 0 divided by 20 minus 0. So now we have to figure those out. Okay, so we'll go back here, and we can do our trace, do a value, and we go from 0, which is going to be our 149.554, and 20 is 200.754. Okay, so, well, let's do our calculation first. How about that? And then we can write it all down at the same time. So we're going to take, we had 200.754 minus that 149.554 divided by 20. So 2.56. So we've got the whole thing now. So now we have, this was 200.754 minus 149.554 divided by 20 was 2.56 pounds per year. Okay, so that's that. This was just our average change there. Now, see, in which year was the per capita consumption closest to the average per capita consumption in the between 1980 and 2000? Well, let's go back to our calculator. And now let's go to Numeric Solver. Now we want to say, okay, well, we want that 169.021, which is our average. And this is going to be set equal to Y2. And let's see what that gives us. So it looks like 11.150. So C is going to be, we've set V of t equal to the 169.021 to see when it was the average. And that is at time equal to 11.150 years. And so 11.15 years, so 11 years past that, that's going to be 91 and plus into the next year. So it's going to be beginning of 1992. And if we take that 0.15 times 12, that's going to be in February, it looks like. So beginning of 92, most likely somewhere in late February. All right, so illustrate the answers from part A, B, and C on the graph. Okay, so let's draw this on the next page. And so we have, let's see, we had our function. So let's kind of get what it all looked like here. So our function was kind of going up from there. We went across and then down. All right, so we won't draw this to scale. So it was a quadratic and it was coming up like this. Then we had some line coming across here. This was our average, and that was what, 169.021. This here part, that was where it intersected. That was 11.151 years. This is years, X. And this was, now we needed our AROC too, our average rate of change. Well, that's going from a beginning, that's not a very straight line, to the end. And hopefully, yeah, I thought that would happen. So that's our AROC, and that was at 2.56 pounds per year. Okay, so that's a straight line. This one's actually the curve, that's a parabola. And so those are all the pieces. So that's the average, and then we have our AROC, and this is just our curve here. And C, that's when it occurs here, the average and the actual curve meet. So that's that time point there. So that's part D. Okay, and so hopefully that helps on both types of those kind of problems. We'll stop there and we'll come back with more.